Now the best way to carry out this check is to check the scheme using the 11-step guide, and when a step is not applicable you just ignore it. So let's carry out this check using the 11-step guide. Step 1, your design objectives. Well, these are specified as life safety. You've got to extract the smoke from the shop unit using a small reservoir before it can enter the atrium. Step 2, your design fire size. You've got to determine the design fire size to be adopted. Now we're told that it's standard response sprinklers that are to be installed, and again the convention to use for standard response sprinklers in this case is a 5 megawatt fire with an area of 9 square metres and a perimeter of 12 metres. This is the general design fire size for a building fitted with standard response sprinklers. So now we know the design fire size, let's move on to step 3, which is working out the mass flow rate of smoke. Now, determine the mass flow rate of smoke. There's 3 models available, and in this case we're going to use this model here. As you can see, this is a fairly simple model with only 3 variables. You've got your QP, your convective heat output, you've got your HO, your height of your opening, and you've got your WO, your width of your opening. This model is presented by the Technical Memorandum 19/1995, issued by the Chartered Institute of Building Surveyors, Service Engineers, and PD 7974 Part 2. Let's put in our known variables. Now we know the convective heat output is 5,000 kilowatts or 5 meg. Now we need to know the dimensions of the openings. In this case, the width will be 11.5 metres and the height is 2.4 metres. So put them in the variables in. You'd have got a mass flow rate of smoke leaving that shop 18.81 kilograms a second. That's the mass flow rate of smoke. Now there is a downstand, and this will cause more entrainment of smoke as it passes under it. So it's conventional to double the mass flow rate of smoke if there's a downstand. So in this case, you should assume that the mass flow rate of smoke out of this shop is 18.81 times 2, which gives you 37.62 kilograms a second. So that's the amount of smoke we've got to assume is coming out of that shop into the small reservoir. That covers step 3. Let's move on to step 4 now, determining the temperature of the smoke. And this is a formula to apply. Theta equals QP divided by MC, where your theta is your temperature rise in Kelvin, QP is your convective heat output in kilowatts, M is your mass flow rate of smoke, and C is your specific heat capacity. If you'd have put all those known variables in, you'd have got this. A theta value of 132 degrees Kelvin. That's the temperature increase. That's the temperature increase. We need to know the absolute average temperature of the smoke, and you'd use this formula here. TL equals TO, which is your ambient smoke temperature, plus theta, your temperature increase. This would have given you a value of 420 degrees Kelvin. That's the absolute average temperature of the smoke. Now again, this is a high temperature, as you would expect with a 5 megawatt fire leaving the opening, as there is not much entrainment. Even though the entrainment's been increased by the downstand, it's still not as much smoke coming in there. This is not a problem though, again, because the temperature of the smoke will not affect tenability in the shop, as the shop should meet acceptable travel distances. This is about getting the smoke out of the reservoir with the tenability limits. The shop should have already been evacuated. In other words, you've met your acceptable travel distances. That covers step 4. Let's move on to step 5 now, the stratification. Now in this case, clearly, as they are extracting it in a small reservoir outside the shop, stratification is not going to occur. It's not a problem, so you can ignore it. Let's move on to step 6, which is the ventilation requirements. In this case, the ventilation requirements are to extract the smoke in the reservoir located outside the shop. Now we know how much smoke is to be extracted, and this is 37.62 kilograms a second. Now we've got to convert this to a volumetric flow rate, taking into account that the fact that the smoke will be very hot and will have expanded quite considerably. So we know how much mass flow rate of smoke. We need to work out the volume of smoke. This is a formula here. V equals M divided by rho 0 times TL divided by TO. If you'd have put those in, the known variables, you'd have got 45.7 cubic metres a second. So the volumetric flow rate of smoke leaving the opening is 45.7 metres cubed a second. Now we've got 4 fans rated at 12 metres cubed a second, so that's 4 times 12 is 48. We can be confident that the smoke will be extracted. So we have got enough fans and they've got the right rating. Now we need to ensure that the containment screens are deep enough. So how deep do the containment screens do? Well, to do this, we need to determine the depth of the flowing layer in the reservoir and ensure that the screens are deeper. So we've got to work out the smoke layer depth. And the depth of the smoke layer can be calculated as follows using this formula here, where dB is your flowing layer, depth under the ceiling or balcony. Your CD is a coefficient, and this is 1 if there's no downstand present and 0.6 if a downstand is present. Note, again, the subscript B can be replaced with an L to ensure that you can apply it to any smoke reservoir or flowing layer. Now, MB is the mass flow rate of smoke. TB is the temperature of the smoke. L is the separation distance of the channeling screens. Theta B is the ambient temperature increase. TO is the ambient temperature, and it's usually 288 degrees Kelvin. So let's put in our known variables as shown here. When you calculate this out, you should have got a dB of 2.2 metres. That is the depth of the smoke layer. Well, now we need to determine the additional deepening. As the smoke hits the forward screen, it might cause some additional deepening, so you do have to work out if there's any additional deepening and how deep it is. This is a formula to apply here, where delta dB is the amount of additional deepening. HS is the height of the underside of the ceiling above the base of the fire. Your dB is your depth of your smoke layer, and your WB is the distance from the opening to the containment screen. Now, when you put those in, you should have got a delta dB of 0.233 metres. That's the additional deepening. About 23 centimetres is going to be the additional deepening as the forward emphasis of that smoke hits the screen. So you've got to increase it. So that means you've got to add that to the additional flowing layer depth. It gives us a depth of the containment screens at minimum of 2.433 metres. That's without any safety factor. So it is recommended that you also put a factor of safety in, possibly 10 centimetres minimum, but you should consider putting in some additional factor of safety in the additional screens. Now, where do you locate these ventilators? Well, before you do this, you carry out step 8, which is the stagnation check. Well, again, the stagnation check only applies to natural ventilation. We're using mechanical extraction, so you can ignore this step. You don't have to carry out step 8. Let's move on to the next step, though, the plug hole in check. Now, this does apply to both natural and mechanical ventilation. You've still got to apply mechanical ventilation. You've got to check the plug hole in. Now, don't forget there's two models to determine if plug holing will occur, and this depends where they are located. Now, the model to use when the ventilator is more than 2 metres away from the edge is as shown here. This is the formula, the MCRIT formula, when it's more than 2 metres away. Now, if you put all your known variables in, you would have got an MCRIT of 18.96 kilograms a second. That is the maximum that can leave each fan without plug holing, 18.96 kilograms a second. That's the critical exhaust rate. Now, we need to ensure that the fans, the actual max smoke leaving each fan does not exceed this. So we've got the critical exhaust rate. Now we need to know how much smoke will leave each. Now we know the fans are rated at 12 metres cubed a second, but we need to convert that to a mass flow rate of smoke so we can compare it to the MCRIT. So we've got to convert that volumetric flow into a mass flow rate using this formula here. MCRIT equals V fan times TO times density O divided by TL. If you'd have put them in, you'd have got 9.8 kilograms a second. So that's the mass flow rate of smoke leaving each fan, 9.81. We know the critical exhaust rate is 18.96. We're going to get 9.87, so we can be confident that plug holing will not occur. So that covers that step. Plug holing will not occur. Now, step 10 is to check the air inlet velocity if required. You've got to make sure that the replacement air coming in through the exit doors and any automatic opening doors or vents is not so high as to impede escape from the building. And in this case, it's a shopping centre, and we said we've got an inlet area of 12.5 square metres. Now, the maximum velocity that is allowed for the incoming replacement air for a public building is 5 metres a second. And again, general public. So now we need to check what it will be, the air inlet velocity using this formula here, where the area of inlet must be greater than or equal to Vmax divided by UCI, which is your coefficient. Now, if all the fans are operating at 12 metres cubed a second, it gives us a total extraction rate of the Vmax will be 48 metres cubed a second. If all four are running, which we've got to assume, we're going to get 48. Put the 48 in the formula. We know it's 5 metres a second is the U, and it's the inlet efficiency is 0.6. We're saying the 60% efficient. We need an AI of over 16 square metres. And this tells you that if you've got less than 16 square metres of inlet air to replace the smoke that's been extracted, the velocity of the inlet air will exceed the acceptable velocity. In this case, there's 12.5 metre squares of inlet proposed. Clearly not sufficient. You need to increase it by at least 3.5 square metres to ensure this particular step is accepted. That's the answer to this. You have to increase the inlet area to ensure that the 5 meters a second is not compromised. Now that completes this step. Move on to step 11, which is your post-design considerations. In this case, your weather conditions, not relevant. Certain ones aren't relevant. You've got to make sure they're tested correctly, maintained correctly. Complete step 11 in this case. And that completes this exercise.